Functions of registers in a CPU. Imagine trying to solve a math problem without being able to jot down intermediate calculations. Frustrating, right? In a CPU, that's the role of registers. Small but mighty storage locations that act as the CPU's scratchpad, enabling it to process data and instructions at lightning speed. Today, we are exploring the fascinating world of CPU registers, their types, and their critical role in powering your devices. Registers are the fastest memory elements in a computer. Located within the CPU, they temporarily hold data, instructions, or addresses while the processor works on them. Think of them as a chef's cutting board, keeping ingredients close and ready for use while preparing a dish. Without registers, the CPU would have to rely on slower memory systems, and that would significantly drag down performance. We can first check the types of registers and their functions. First one, general purpose registers, the all-rounders. These registers are the multitaskers of the CPU. They hold intermediate data and results during computations. Programmers or compilers can directly access them to store temporary data. For example, in 86 architecture, you may encounter familiar names like EAX, EBX, ECX, and EDX, each ready to take on a variety of tasks. Second one, special purpose registers, the specialists. These registers are like experts, each with a specific role to play. First one, program counter, the navigator. This register keeps the CPU on track by holding the address of the next instruction to execute. It's automatically updated after each instruction, ensuring smooth program flow. Second one, instruction register, the translator. The instruction register holds the instruction currently being executed, acting as the bridge between the control unit and the rest of the CPU. Third one, stack pointer, the organizer. The stack pointer keeps track of the top of the stack, a reserved area in memory used for managing function calls, return addresses, and local variables. Fourth one, flags or status register, the monitor. This register acts like a health tracker for the CPU, indicating the outcome of operations. For example, the zero flag tells if an operation's result is zero. Carry flag highlights whether an arithmetic operation generated a carry. Sign flag indicates whether a result is positive or negative. Moving to the third type of register, data registers, the workhorses. Data registers are optimized for speed, temporarily holding operands for arithmetic or logic operations and storing results. Their rapid read and write capabilities make them indispensable for computation. Fourth one, address registers, the GPS system. These registers handle memory addresses, enabling the CPU to access instructions and data stored in main memory. Examples include memory address register, holds the address of the memory location to be accessed. Memory buffer register temporarily stores the data being read from or written to memory. Fifth one, accumulator, the core calculator. The accumulator is the go-to register for storing results of arithmetic and logic operations. It's like the CPU's primary tool for calculations, frequently used for operations involving implicit operands. Sixth one, floating point registers, the scientists. These registers specialize in storing and processing floating point numbers, crucial for tasks like scientific computing, graphics rendering, and machine learning. Seventh one, control registers, the managers. Control registers govern the CPU's operational settings and state. For instance, in 86 processors, registers like CR0 to CR4 handle features such as memory paging and debugging. Eighth one, segment registers, the address keepers. In processors with segmented memory architectures, Segment registers store the starting addresses of memory segments. In 86 architecture, for example, ZS code segment points to the segment containing executable instructions. DS data segment points to the segment containing data. Now we can check the general function of registers. So how do registers contribute to the CPU's operation? Let's break it down. First one, instruction execution. They store instructions fetched from memory, hold operands for operations, and keep the results ready for further processing. Second one, data transfer. Registers act as intermediaries between the CPU, memory, and I/O devices, facilitating smooth data flow. Third one, memory addressing. They store memory addresses, allowing the CPU to locate and access required data or instructions. Fourth one, status monitoring. Using flags in the status register, the CPU keeps track of the results of operations and adjusts its next steps accordingly. Fifth one, speed optimization. By reducing reliance on slower main memory, registers drastically enhance the CPU's execution speed. Sixth one, control and coordination. Registers like the program counter and stack pointer ensure orderly execution of instructions, including jumps, loops, and function calls. Next, moving to the characteristics of registers. Let's not forget what makes registers special. High speed. Registers are the fastest form of memory, far surpassing RAM or cache in speed. Small size. Limited in capacity, they typically range from 8 to just 64 bits or more. Direct accessibility. The CPU can access registers instantly, which is critical for performance. Architecture dependent. The number and type of registers vary depending on the CPU design. In the grand symphony of a CPU, registers are the unsung heroes. They are the workspace where instructions are decoded, data is processed, and results are stored at all blistering speeds. Understanding their roles help us appreciate the intricate choreography that makes modern computing possible. The next time you use a device, remember, it's the registers that keep the magic flowing.